Nice to be on CodeMesh again as a speaker. I've not been here for a while. Today we are talking about embedded systems and how you could do them with a functional language like Erlang and what we actually did in this space to make it easier to do this. So my name is Stritzinger, to have it pronounced once correctly. I'm the owner and founder of the company who is actually doing this. And the slides are also by Adam Lindberg, so I stole half of his slides, and so I didn't want to keep him unmentioned. So the whole thing started basically, that's where it started. I always show these old slides because that's how we started. Getting into, oh, they're reformatted again. The problem is Adam uses widescreen, and I had my slides on 4:3, and so the lining is a little bit off now. It's design, it has to be so. A few years ago, or actually many years ago, we started building these boxes, which are for the automotive space to reflash automotive ECUs when they are still in stock. So you need lots of channels, and you need to actually have implemented all the automotive protocols. And for the second version, actually, that's the third version. We are now at the 3.5 version. I was kind of bored writing all this stuff in C, all these protocols, and all this configuration file reading, and it's all a lot of work. And so I tried out Erlang, and that was 2007, and there was no going back. That's how I started Erlang. This box started it. This box uses Erlang to implement all these automotive protocols, but for the low-level stuff, we can't use Erlang there. So we have basically a mainboard where Erlang runs on FreeBSD, and then we have custom-made gateways which have all the hardware for the automotive protocols. And we run RTEMs. You will hear about RTEMs a little bit more later on these little boards. And the little boards are written in C. And the main application is basically just dump queues, getting the packets from USB, shoving them on the CAN bus, for example. So as minimal as possible. Which obviously didn't work because you have lots of latency issues there, so you implement more and more and more in the gateways for performance reasons, because like the time it takes to flash is kind of the only thing that's important to our customers. Does it work, and how long does it take? Since we kind of want to get out of C programming, or only want to do C programming to do more Erlang programming, we need to get Erlang closer to the hardware to get rid of these latency things. I'm talking a little bit about hardware this time, about components you can plug into the hardware, about the software, and about the future. So GRiSP is actually a software stack, but nowadays we made a board to actually support this software stack and to make it easy to get started quickly. Because if you have a new embedded board, you have to write lots of drivers to actually get it out of reset and adapt all the things. And we could have used the existing board like BeagleBone or anything. And then we had to write exactly the same amount of drivers, or maybe even more to do so, because it's a much larger CPU. But we decided to have our own hardware, because then we can decide when we have to rewrite the drivers, and not somebody else is deciding, yeah, we make a new version. Oh, all my drivers are broken. So that was the initial thought about why do own hardware. So this is the hardware. You see also one board on this little card in the front. I will explain the parts of the hardware. Size of the board you can see about here. It's made so it's as easy as possible to actually do embedded stuff or cyber-physical stuff or what buzzwords? Internet of Things stuff. Did I cover all the buzzwords? Industry 4.0, yeah. As it gets started as easy as possible and basically stay on the Erlang side as much as possible. So most people can actually do things with the board without touching, without ever writing a line of C. And if you also add a little bit of C, then you can do much more even. So the thing is an embedded wireless device. It has Wi-Fi on. So we decided, Ethernet is kind of boring, let's put Wi-Fi on. I can tell you we paid dearly for that. This is the main cause for the 1-year delay is the Wi-Fi thing. And actually not the antenna, that was only a few weeks, but USB on the main chip was broken, and so we had to kind of work around that. And yeah, we basically, I should have announced that we are selling the board soon, a year ago, so we are kind of late. It runs normal Erlang, not a reduced VM, it's just the Beam. The Beam as you know it, with the same features, and it runs Erlang on real bare metal. So what this means exactly, I will explain later. But as close as possible as you can get the Erlang VM to the hardware without an operating system going in between and holding up things and delaying things, increasing latency and getting less real-timeness. It has a lot of connectors. I will explain the connectors later also, to plug in sensors and actuators. And we use the standard, which I also will tell about later. The CPU we used is a kind of medium-sized CPU. The reason we didn't get put on a larger CPU, because some people in the mailing list asked, yeah, I can get a Raspberry Pi with 1.2 gigahertz for such and such euro. Why would I spend more money to get a smaller CPU? Well, it's a prototyping board. It's actually it's not a server. And the Raspberry Pi is a little server or a little desktop computer. The reason we got this medium-sized thing, so it's very easy to get an Erlang application on. It's not like constrained from the size or from the compute power. But it's also not so fast that you can't run it from a battery for a long time. I mean, these batteries run forever, basically, with the GRiSP board, the normal USB batteries. We have 60 megabytes of RAM, which is actually plenty. The reason why we have so much is I actually can't buy smaller ones. If I take SD-RAM, we have Wi-Fi on, as I already mentioned, and basically the disk is a micro SD card. So micro SD card is for playing around. Tome is very good, so you can quickly switch the card and have different demos, for example, on a talk. We have a version of the hardware basically for industrial use where we don't use micro SD cards because they fall out and they have all kinds of issues. Where we actually have NAND flash on a board using the same software stack. But then you need a flash file system, and for the flash file system you need a license, and they are dual licensed. And if I do a commercial product, that's fine, because then I just pay to get rid of the GPL 3, 4, 5, whatever they have. But we didn't want to basically embother this on the users. And if you use SD cards, you get the flash file system or the flash mapping thing for free, and you can just run a fat file system on top of it for easy access. So let's look at the parts of the board. We have a CPU, that's the thing here, the second largest thing here. The other thing, I think there would not be an extra slide. This large thing is the USB controller we needed to add, because you need an external USB controller, because the darn CPU USB was broken. It did not work, and Atmel admitted this. If you use external memory, the USB doesn't work. And we don't know how to make it work, too. That was basically the main reason for the 1-year delay. Otherwise, the CPU is quite good. It's an ARM Cortex M7, which is basically the M line of ARM is for mobile. For smaller things and less energy things. M7 is the largest one of this line, if I remember correctly. There might be a newer one, but I don't. So it's from Atmel. It can run up to 300 megahertz. You can run it slower if you want to conserve energy, of course. And it has a built-in FPU, which is kind of convenient, since Erlang kind of expects that there's an FPU. Which is not every embedded processor has an FPU on. Lots of very small ones don't have an FPU, so you have to use software FPU. And then better don't do too much calculation, because software FPU is very, very slow. And it has some digital signal processing extensions, which we plan eventually to actually map to the Erlang side with NIFs, so you can actually use them for like little signal processing things or calculations for control loops or whatever. It has also internal memory. It has a 2 megabyte NOR flash, basically, which you can boot from. And it has 384 kilobytes of SRAM. So this is too small to actually run Erlang, the whole Erlang VM in. But actually, we can, the next thing we are looking at are controllers which have enough flash and RAM inside, where you can actually then run Erlang on the system on a chip. So watch this space in the next years, maybe. Because we have use cases for this. The flash is used to actually for the bootloader. So we have a little bootloader which also uses the same operating system with quotes as the actual software. So the bootloader is by us. And the bootloader basically just looks at the SD card, has an SD card driver, looks for an INI file on the SD card, and then does whatever you tell it in the INI file, which then usually is boot your beam into the other memory, into the other RAM, because the 348 kilobyte SRAM is also a little bit little for beam. But this SRAM has an advantage. It's unused at the moment. It's free. It's open. So we can do things with it. And of course, it's also very fast because it's inside the CPU, so there is no wait cycles. So we will probably map the inner loop of the Erlang VM into this SRAM on chip and make the whole VM run faster. And for that, it's actually kind of largish already. The external RAM I already mentioned. It's the little thing on the side here. And the micro SD I also mentioned. So external RAM is, to say again, 64 megabyte SDRAM. We also have 2 kilobyte EEPROM for like storing the serial number or some configuration which you want to store per board, for example. So we store our logistics stuff, but the user can also store configuration things inside. And we basically support normal micro SD cards. The Wi-Fi is the little module here in the corner, and that's the antenna. So by now we have actually decent range with the antenna against an access point. I also added for special uses the possibility to solder on a plug instead of the antenna, basically. So you have to be good in soldering than to solder on these antenna plugs, and then you can plug in a larger antenna and get whatever range you want. Not whatever range you want, but much more range. So we support 802.11n, 2.4 gigahertz only, up to 150 megabits per second, up to. We can actually copy that fast with the CPU. So I don't have measurements because the current performance, the real performance we were happy we got it running. The performance will improve in the future because there's room for improvement. In the USB driver, you can use more buffer descriptors to actually copy more. And so, but we already have a driver that does DMA and kind of does the decent thing. It just needs a little bit of tweaking to get actually more out of it. But for the most applications, you don't need that much bandwidth. Otherwise, maybe if you want to do camera things, but that's actually not the board to actually hook a camera to. I mean, it would work, but that's not my main application I thought about. You can save power, so it's an embedded CPU, so it has all kinds of power saving modes. You can switch off parts of the CPU. You can also switch off the Wi-Fi chip, because that's the big power drain, which is kind of constant. So you can sleep your CPU all day. If your Wi-Fi is on, that doesn't help at all. So there's basically a switch where you can actually switch off the power of the Wi-Fi. So let's talk a little bit about these black connectors around the top and part of the right border. We have these plugs are actually according to a standard, which I will talk later to. So you can get basically ready-made sensors for these plugs, but you can also use the wires by yourself. You can just hook in these little patch cables and wire to your breadboard and do whatever you want. So the first port is the GPIO port. The second one is also a GPIO port. You can't have enough GPIOs. GPIO means general purpose I/O. So you basically have a few lines which you can switch on and off, and you can switch them like open, so floating. You can configure them in all kinds of ways. You can usually, on all these lines, you can basically say, yeah, I want this to be an interrupt. So wake me up when something happens on this line. And by the way, all the connectors can be GPIOs. So if you don't need the other ones and need lots of GPIOs, you can configure them. And then just the writing on the connector is not correct anymore, because then it's not an SPI, but a GPIO. So every pin on the CPU basically can be GPIO. Also wired to pins on the GPU, we have RGB LEDs, 2 LEDs, I mean, to indicate. So you see one green here, that basically means my application has booted. Or you can do blinking lights and whatever things. You also want to have maybe a few configuration switches or input switches to play around, or to actually start the server. I didn't implement that. You could have used that for the robot to basically say, okay, now stop moving, sleep. 5 switches. You have a reset button, which is always very convenient during development. Reset is very much nicer than unplug, plug. Because if you unplug, plug, then your serial line goes off, and that's not good. So reset button. The GPIO will get drivers. I say will get because it's not done yet. Pulse width modulation drivers, and probably also sigma delta things for actually controlling the speed of a motor, or the servo motors which take pulse width modulation as a signal, basically to say where it actually needs to go. Long pulse goes over there, short pulse goes over there. Because the pulse width modulation is kind of time sensitive and needs to be pretty quick, it's not good to do this in Erlang, on the Erlang level. Not yet. There's one plug which is called UART, which is a 3.3 UART, so it's not like the normal serial connector we had on the PC like ages ago, or you can still have as a USB serial, but you can plug in a converter that makes it to have the normal, because the normal thing is plus minus 12 volts signal strength, and there's also standards for industrial things, so you can get all kinds of converters here, and there are a few P modes where you don't go all the way to 12 volts, but you directly plug it in, and the P mode also talks 3.3 volt. For example, the ultrasonic sensor on the front of the robot, that's one of those UART plugs. It's hooked into you can see it here. It's hooked into the UART plug, and the motors are wired to the GPIO. The UARTs are actually more flexible because it's actually an UART, which means you can configure it in all kinds of ways. You can implement all kinds of other protocols, serial protocols. There's actually a little serial protocol engine on the end on the CPU, so you can actually do bit streams which are configurable. You can do HDLC or whatever. SPI, I will explain what SPI is. Serial peripheral interface. For the SPI, we have 2. SPI is a synchronous protocol, which is very, very, very primitive. So it's very easy to actually put on a chip. And it's actually easier to put SPI on a chip than a lot of pins. Because SPI sends the bits for the pins that you normally would have serially with a clock, and you have basically a lot of chips that you can hook directly to an SPI, so there's a lot of P modes that actually use SPI. And it's also pretty fast. You can actually clock it up to 20 megabits per second, not bytes, megabits per second. After that, it kind of breaks down. It's a master-slave protocol, so the CPU is always the master, so basically telling the peripheral what to do. And you have one chip select telling the peripheral, yeah, I'm talking to you, by the way. One clock line, which is basically, yeah, here are the bits. And 2 lines there, one out, one in. Very easy. And then you can configure like on what clock phase the bits get shifted and stuff like this, which makes it complicated again, by the way, because in the chips you get all 4 combinations of like first edge, second edge, phase shifted, polarity, and power and ground. I mean every PMOD connector has power and ground. So you have a 3.3 volt power on the connector actually. The ICRC is actually in the middle of the board, here in this little circle, because ICRC is a bus, and normally you have these ribbon cables where you can have multiple I/O things on one I2C and you plug them in a chain. I2C is similar to SPI, but different. It has only one data line, and the clock line stays the same. It's addressable, so we don't need the chip select line. And because it's addressable and it's a little bit more complicated protocol, you actually need only one data line because you basically send a read, address, and then the chip basically sends the answer back after you're finished. However, so the advantage is addressable, so you can have much more I/Os on one board. The disadvantage is it's slower. It's limited to 400 kilobit per second. There's also a connector on this for one wire. One wire is actually similar to I2C, but for longer wires, you can say. And for more addresses, because in longer wires, you could have actually more plugs. Because I2C only has a bytes address, and many chips have fixed addresses built in, or a group of fixed addresses, so you can actually tweak a few bits of the address, and the rest is fixed. And so occasionally you get conditions on the I2C, and then you have to actually see how to manage the different hardware. Dallas one wire is actually a lie, because it's not one wire, because you always need a ground layer, but it's ground plus one wire. And marketing made one wire out of it, probably. So you have only two wires, and you have your power over these wires and the data. So you can have like simple sensors, like temperature sensors or something. You can actually power from the line. So you just wire them, and it's also a bus. It's called addressable micro LAN. Was the other word the marketing of Dallas coined back then. You can have lots of, I think, 70 sensors on one wire. And the sensors, which was the actual new technology back then, have a 64-bit unique ID burned into the sensor. So you always know every sensor is different. And what you normally do, you hook them one by one and then see who shows up, because you can search for new IDs. Who shows up here? And then you can actually say, this is like topmost, lowermost. There are all kinds of things. You can get sensors for this. You also get security devices for this. It's kind of a side business of Dallas, because they made access control devices out of one-wire plugs, which are actually still in use. I think the Turkish subway system still uses a one-wire plug. So you can actually make a door opener with it. And there's lots of like encrypted memory, or memory you can only store keys in, and basically have the crypto primitives on the memory. So we could also think about like making a little board on top of the one wire to store, let's say, your web server certificates. Should be possible. I thought about it at least. There's a micro USB on one side, but the micro USB is only client, so we're not host. The micro USB is used for three things. The power comes over it, so we just power through USB. If you don't have a totally wimpy laptop with very wimpy USB plugs, you can just plug it into your laptop and it gets powered. Some laptops are a little bit weak on the USB, especially with the voltage goes down and everything. So if you do Wi-Fi and a lot of peripherals, you might want to use a hub. So on my laptop, it just works without hub. On the USB, there's two USB serial connectors, basically, or units. And one is for the console. It's always nice to have a console, so you can actually watch things booting. And if the Wi-Fi doesn't work, you can actually try to configure it. I mean, you have to get into the thing for once, and you want to actually see what's wrong when it's not booting. So serial console is always nice. And there's also a JTAG debugger on the device. So JTAG is a kind of standard where to actually test chips. But you can run a debugger with it. So you can single step and breakpoint the actual CPU. So you can, from reset, debug the first steps of the CPU with JTAG. And we built a JTAG debugger interface on the board. So all you need is a USB cable and a piece of open source software, which is called OpenOCD. And then you can flash the bootloader also and do all kinds of things. There's also a real JTAG connector there, because the OpenOCD JTAG is kind of limited. And if you have a real JTAG debugger plug, which costs about 2K if you have a good one, then you can do much more things even. You can configure all kinds of things, and it's much smarter. And you have a backtrace in the debugger. You can actually see after the crash, actually, how did we get here? Which is very, very useful sometimes. So that's basically the parts of the hardware. Then a little digression. We basically, the actual software stack or the actual idea to run Erlang on the hardware was actually done for this device. It's for Bosch Rexroth. They actually paid for the first Erlang port on Artems. So the actual computer is only this part. That's only cables here. So cabling always takes a lot of place here because there's lots of connectors in here. So the CPU is only in this like this size. And that's the thing that's actually used. And it's used for, here in the prototype, for industrial transport systems, which is the things that move around. So this is all controlled by 15 Erlang nodes, which you can see if you see the green cables here. They plug into the naked boards here. But this was very, very early. Oh, we have sound, yeah. Yeah, I didn't do a real film. We had some test footage, and I just kind of like cut it together and speeded it up a little bit. That's why everybody's talking very funnily. We have our RFID antenna on the systems, and that's the main thing to control the motion and the RFID. So I cut this short now. A little bit more about PMODs. So we saw the connectors that exist, and the PMODs are these little modules which you can plug into this connector. You can get about, PMOD is a standard from Digiland, who also does boards like FPGA boards where you can plug them in, so you can actually get actual I/O into a FPGA board for testing very easily. There are about 100 different PMODs you can buy. A PMOD costs about like between $10 and $25, so they're not that expensive. A little bit more expensive than other sensors, but usually it's a little bit better sensor, so it's more professional. The PMODs, and as I said, it's like this size, it's very small. It's also very easy to make your own PMOD. So if you have any sensor, there's also PMODs for breadboarding, where you can actually solder your sensor on then. And it's very easy, it's a very easy first hardware project if you want to just do just a PMOD. It's a very small board, and it does not have much requirements for hardware, much less than a CPU. So just as an example of the hundreds of PMODs, this is a PMOD to connect actually 4 servo motors, so you can control 4 axes of some model or something to one connector, to GPIO in this case. That's a very nice one, which is new, or pretty new, PMOD nav. It has 3-axis accelerometer, 3-axis gyroscope, 3-axis magnetic compass, and an air pressure sensor, all on one PMOD. And a temperature sensor is also in there too, because you need to calibrate the other sensors. But you can also abuse the temperature sensor. So here actually 11 degrees of freedom sensor thing on one PMOD. That's an older one, which just has a gyro, which is also on the PMOD nav. So we actually, I wouldn't get a gyro anymore. I just do PMOD nav, and we already have the driver. It's very nice. You can measure all kinds of things. That's also an older one, accelerometer, so that's where it started, and now they actually integrate more and more on one PMOD. That's an H bridge, and that's another H bridge. An H bridge is a thing to control a motor. So you can actually, by controlling 2 bits, you can say forward, backward, start, stop. And it's very bad if you have start on and switch from forward to backward, because you get, for a very short time, you get a short circuit between things. So it's, we have a driver to actually take care of this, which stops the thing before you actually switch the direction. And you can get like larger things like a GPS, for example. That's a GPS. It's also a UART PMOD. You plug it in, you have a GPS. So time for a demo. So for demo, we mounted a, let me show you there. So we basically got a ready-made robot kit, which is also available from Digiland, by the way. So we have these 2 wheels and a stem in the ending. These are the 2 H bridges here to control the motors. So that's the HB5 PMOD that you just saw. And here we have the GRiSP board on top of it. And I have 2 batteries on just for good measure. One 6-volt, just normal batteries for the motors, and a USB battery for powering the GRiSP board. So battery is still full, that's good. I put the motors on an extra one, so the motors suck down the battery pretty quickly, and it's kind of sucks when you can't program because the battery is empty. But you could power it from both. It's not a problem. So, and for the demo, I have to pick up my other GRiSP board, which I hid below here. So this is another GRiSP board. Same board here, oops. And it has a PMOD nav on, and we use the accelerometer. That's also just a battery. We use the accelerometer, and both are, by the way, connected to this little Wi-Fi POC here. Where, by the way, anybody has no internet? He's connected to my Wi-Fi. There are several people here. It's not connected to anything except these two boards. It's boring. Just get out. So when I tilt this thing, the robot is supposed to move. So I can go forward, and I can go backward. And if I tilt it like this, it turns. And in the other direction, actually it turns the wrong way around. I have to flip it up. Huh? Does it work like this too? No. No, I need to drive backwards. And by the way, all this is done through Erlang distribution. So I just have Erlang distribution between these two boards over the Wi-Fi, and then you can play with things. So the plan is if you want to do several things, you just put the boards somewhere. Oh, help. Stop. Okay. You just put the board somewhere, and if you don't run the wire, just put a board here and a board there, and then have them network. I'm actually having to change the SD card here to boot the next demo. While we are talking, so where's my little SD card? So that was the one demo. The next demo we will just boot and get through a few slides. So actually, how much time do I have?
You've got 3 minutes until Q&A time.
Okay, so we'll skip to Q&A. I answer all your questions in the talks. I want to talk a little bit about how this actually is made, about the software and everything. Need to reboot this. So I talked a little bit about Artemis, so we can actually skip through this. The important thing is Artemis is not really an operating system where you have kernel mode and user mode, and you have to go through kernel mode, and it preempts you and all kinds of things. It's just a library which you link together with your application, which is Beam in this case, and then you get basically all we get from it is threads and a network stack. That's what we use. You can configure it. It can get very, very small if you leave away the network stack. It gets smaller and smaller. So you can run it on very small hardware, but then Erlang doesn't fit anymore. And I've been told this is called a unikernel nowadays, but it's from the 80s, actually, but it wasn't called unikernel back then. It has a POSIX API, which made porting Erlang much more easier, of course, because kind of everything is there that you expect. Not all the functions work. So it just stops sometimes. So that's the little work we didn't need. Little work, it wasn't little work. It was quite a bunch of work to get the first port done. I just forgot about it because it's years ago. It's very performant. It can very, very quickly switch threads. So if you do a thread switch, it's basically probably even faster than a task switch in Erlang, or at least as fast. It supports SMP, which is kind of neat for a small operating system. So we are actually looking forward to use one of the larger embedded controllers, which have SMP. You can get them you can get embedded controllers with 24 very powerful cores and lots of network IOs, for example. And I'm actually eager to play around with that with Erlang then. Running Erlang on real SMP cores, and would also be nice to show it off, of course. It does not have normal processes. It only has threads. So it's basically, it looks like one operating system process, like a Linux process, running on the real hardware. That's the programming model of the operating system. So everybody shares memory with everybody. There's no protection at all. If you overwrite anything, then it just crashes, or does even worse. It has the network stack from FreeBSD, a pretty current one, which is kind of nice because it's a very powerful network stack. It's actually pluggable. You can also use a smaller one, which is then not as nice, of course. Beam is compiled together with Atom, so you get one image. So when it actually loads a file called beam.bin, while booting. That's basically Artems and the whole beam, and then it just jumps on the beginning and runs through. So that's a little overview. It's like, yeah, beam, application, OTP, GRiSP runtime, runs on top of Artems. Artems sits between the hardware and beam. But actually, that's not totally true, because you can, with NIFs, you can bypass Artems. Since all the hardware registers are visible, you don't have to use drivers, actually. You can, if there are drivers, but if you have new hardware, usually you don't have a driver. And what I'm doing, in this case, I don't write an Artems driver, which I then call from an Erlang driver. I just write an Erlang driver or a NIF and talk directly to the hardware, because it has all the features that you would want to talk directly to the hardware. And only have a little thread to actually catch interrupts and send a message to Erlang and say, hey, there was an interrupt. And then write as much as possible of the driver in Erlang already, because it's much more fun. Actually, the GRiSP runtime, which is the thing that we run on the Erlang side, basically, which is optional but very useful, which should provide a hardware abstraction for all the drivers and the P modes and all the things. It's still evolving, but we're actually pretty happy with the current state already. It provides low-level drivers, the C-level drivers, if necessary, and the high-level drivers for Erlang, and basically a way to load the drivers and register them. As an example, you can do it like programmatically to just add a driver, but you can have just config files, Erlang config file, where you say, yeah, okay, my device is on SPI1, I have a pmod nav, and on the UART plug, I have a pmod max sonar, that's this sonar thing. And that's all you need to do. Then you get a supervisor with the drivers running, and you can just talk to the driver API. And that actually works, what you see here. These are two drivers we actually have. No, I actually wanted to skip these. There's no time, and it's probably also not the right conference here. But deploy, I'm sorry for stealing the logo. So tooling. We have a rebar plugin, which does all the building. And it also has templates, so you can actually do a rebar 3 new GRiSP up. And it basically sets up the normal structure for a GRiSP up. It has some extras where you put your C files. Because if you have a C driver in your application, that actually needs to be linked together or compiled together with OTP and linked together into the beam file, because we cannot dynamic load drivers. We can only statically link all things together. That's why we have rebar 3 GRiSP build, which basically pulls the source code of OTP, patches all your drivers in, and then builds OTP from rebar. And then it uses this OTP to build your stuff, or to actually build your, and it packs it together in a release. If you do rebar 3 GRiSP deploy, does this. And you can have actually plugins where you can actually say, yeah, my path to my SD card is here. And before copying to the SD card, erase the SD card, and after it, eject it. So you just do rebar 3 deploy, and then you pull out your SD card and shove it in, and it just works. There's probably no time for demoing this. Actually, it doesn't work on my laptop because I kind of screwed up my laptop yesterday. I'm not usually working on the laptop. It only goes to conferences. What does this slide do here? I don't know. This slide doesn't belong here. Second demo. Do we still have time for a demo?
2 minutes. 2 minutes?
10 minutes? Oh, plenty of time for a demo.
Pronunciation.
2. I heard 10.
Details. Details.
So let me. Oops, no, that's the wrong connector. I don't actually have the HDMI. Where's my HDMI? It's the wrong way around. Running out of space here. Do you see anything? No, not.
Yes.
Yep. Is it readable? No, that's the wrong. So who is this guy? Let's see, how many do we have? No time. So it blinks, so it's ready. I'm doing, this is a remote shell to the actual GRiSP node. So this shell is on the robot, and the other window I want to have is my netload window. So I start another Erlang node and I connect it to the, oops. Oh, 6, can't type. Okay, we are connected, and so I also want to, actually, because I tweaked the demo for the carpet here, I do a quick load over the network. So I'm now basically loading the Beam file from this laptop while the software is already running. So we can tweak it afterwards. Not much time for this. And then I just start it here. So follow me. Oh, actually, I can show you other things. Yeah, follow me. And so I wrote a little function like forward for 200 milliseconds. And it drives forward for 200 milliseconds. And of course, we can also drive backward. And you see it behaves weirdly on the carpet. Yeah, come in front if you want to. We have the video now from front, so don't. And we can turn. And we can turn also to the right. And I also have a little algorithm running. So now it's looking for me. I have to go there, so otherwise it finds the table or something. And when it found me, it comes towards me and follows me around.
It's harassment.
So there you see the distance. So here on the beamer, you see the distance the ultrasonic sensor is basically seeing in inches, by the way. That's how the sensor works. And literally, we coupled this together on Monday before I flew out this. Like when the driver was working, I had 1 more hour, and so it's very easy to. So I will leave it. Let's see what it does. So the final remarks. Hello, Beamer. What's it doing? Scary. Help. It's hunting me down. Oh, please. I want to show my last slides. Just a few. There we are. So, just a few slides on the future. Where are we going? The immediate future, I'm very happy to announce, like with 1 year delay, we will ship in the middle of November, and we will have software 1.0. The software is already on GitHub, so you could have watched it, how it's developing all the time. So development model is totally open. We have all our issues on GitHub, also our internals, so you can actually watch us work, and also help us pretty soon when you can get the boards. So yeah, hardware ships very soon. I heard that the hardware should be arriving at our hardware developers today, or tomorrow, and we will get the hardware next week, and then we will ship the pre-orders as fast as possible. The next step is, which is already in the pipeline, or that's actually not next step, that's 1.0. We will have VPA 2, because it kind of sucks that they have these open access points to actually play with it. But it was a lot of work to get all these VPA supplicant thing running on RTEMs. And unfortunately, it's not crack attack proof in the first version, but I promise you, version 1.1 later this year will be crack attack proof, because we are actually moving to the latest FreeBSD version of VPA supplicant. But for that, we need to move other things. We currently have Erlang 19.3, and we have all the basic C-level drivers for all the PMODs and one-wire. Those already work, so actually no C required anymore. And we are busy writing drivers for the higher level PMODs, so the most important ones, et cetera, et cetera. The board is also used in the Litecoin U project for edge computing and Internet of Things applications, which I need to mention here. Actually, sorry about the missing U flag. No, really, it's mandatory, actually. I just remember that. The roadmap, Erlang 20 is soonish. Erlang 20 is like we also go to multi-threaded mode then, because currently we are using single-threaded, but since it's not the default one for Erlang 20, we basically want to go with the stream. And also I want to play with this SMP embedded controllers. So Erlang 20 soonish, more drivers, of course. And we have one project starting to actually have the possibility to write hard real-time processes in Erlang. And if you want to know how this works or how this might work, you can talk to me afterwards. And there's also raffles. If you're not on the mailing list yet and get on the mailing list during the conference, you can win a GRiSP board, one of 3. It's getting less and less with every conference, but we have it on the roll-up. So every time I bring the roll-up, I have to give away a few GRiSP boards, otherwise I'm lying. And also to actually boost up, because lots of people pre-order the board and have been waiting for a while now, so I'm very sorry about that. To actually, is this readable? Yeah. So basically every board ordered in the past, up to December 6th, we will actually raffle 10 PMOD NUFs, 1 of 10, of course, and 1 robot kit, like one kit where you can build this out of. But it will be actually probably another one with servo motors, which actually is better because then you can control them more easily, because this is moving too quickly. Yeah, questions? No time for questions. Ask me afterwards outside. Okay. Sorry about the day.